We have seen how the Carathéodory extension theorem and the Hahn Kolmogorov extension theorems can be used to upgrade an existing outer measure or an existing pre-measure to a full measure, and using this prescription we can actually give many examples of new measures on the Euclidean spaces Rd and also other spaces. But for this lecture we will restrict ourselves to Rd. So x equals Rd for this lecture, and we will see how we will see how the Hahn Kolmogorov extension theorem actually gives you the Lebesgue measure. We have seen from the Carathéodory extension theorem, we get from the Lebesgue outer measure, we got the Lebesgue measure. We proved in the last class that the Carathéodory measurable subsets are exactly the Lebesgue measurable subsets. So the restriction of the Lebesgue outer measure to both these sigma algebras is the same, and this is the Lebesgue measure. But in fact, remember that we had a definition of Lebesgue outer measure using the elementary measure, and I claimed in my last lecture that this passage from the elementary measure to the Lebesgue measure is given by the Hahn Kolmogorov extension theorem. So in this claim it is implicit that the elementary measure should be a pre-measure. This should be a pre-measure on a Boolean algebra, and the Boolean algebra we will take is the elementary algebra. So if we prove that the elementary measure is a pre-measure on the elementary algebra, then using the Hahn Kolmogorov extension theorem, it's not difficult to show that one gets exactly the Lebesgue measure when you apply the Hahn Kolmogorov extension theorem. So let's see first that this lemma that Rd equipped with the Boolean algebra ERD bar. So this was the elementary algebra of elementary or co-elementary sets, and equipped with this M bar, which was the extended elementary measure given by ME if E is elementary and plus infinity if E is co-elementary. So this gives us defines a pre-measure space, meaning that M bar from this elementary algebra to this non-negative extended reals is a pre-measure. So let's prove this. So we already know that the elementary measure on elementary subsets is finitely additive. So if E and F are elementary and disjoint, then M of E union F equals ME plus MF, and this is the same as saying that M bar of E union F is equal to M bar of E plus m bar of f. So this implies that m bar is finitely additive measure on elementary sets. Similarly, if any one of E or F is co-elementary, then E union F is co-elementary, and so we get plus infinity, which is the measure of E union F, and this is m bar E plus m bar F. This is also plus infinity because either m bar E is plus infinity or m bar F is plus infinity. M bar E is plus infinity or m bar F is plus infinity. So it is means that m bar is finitely additive on E bar of Rd. So you have a finitely additive measure on the Boolean algebra of elementary and co-elementary sets. So now let's prove that m bar is a pre-measure, which means that if you have a countable infinite collection of elements of the elementary algebra such that the union itself is either elementary or co-elementary, then you should have, if in addition they are disjoint, so one should also assume disjointness, then this implies that the measure of the union is the sum of the individual terms. So this was our definition of a pre-measure. So now let's analyze what kind of unions are possible. So let's divide them in cases. So if all ENs are elementary, then union of n equal to 1 to infinity can be either elementary or co-elementary. So this is an observation, either elementary or co-elementary. So how can we show this? So we are just going to give examples. So example, if En is given by let's say 1 by n and 1 minus 1 by n. So this implies that the union of ENs n equal to 1 to infinity is nothing but the open interval 0 1. So one should check this, that you get the union of the open interval 0 1. So it is elementary. So in this case you have countable union of elementary sets can be elementary. So countable union of elementary sets can be elementary, and of course if you have a countable union, you can make it a countable disjoint union and the sets will still be elementary, and so even a countable disjoint union of elementary sets can be elementary. Now if we take En to be minus n minus 1 minus n union n plus 1, then this is an elementary set, but the union of En's n equal to 1 to infinity. So here n is greater than or equal to 1. So the union of En's is nothing but minus infinity to minus 1 union 1 to infinity, and so this is a co-elementary set because the complement, this complement is nothing but the set minus 1 1, which is elementary. So this means that countable union of elementary sets can also be co-elementary. So countable union of elementary sets can be co-elementary. So in both cases we have to show that when you have disjoint union of elementary sets which are either elementary or co-elementary, then you have this relation which is the countable additivity relation. On the other hand, before I prove that, notice that union of co-elementary sets can never be elementary, because each of them is unbounded and the union is bounded, so which is a contradiction. So union of co-elementary sets can never be elementary, but the union of co-elementary sets can be co-elementary, So in this case, for example, if you take En to be minus infinity to minus n union n to infinity, then En's are co-elementary and the union of En's n equal to 1 to infinity is again co-elementary, because if you write this as E complement is nothing but the set minus 1, the interval minus 1 to 1. So it is the complement is elementary, so it is co-elementary. So we see that union of co-elementary sets can never be elementary, but it can be co-elementary. So for the second case, in this case, if En is a disjoint collection of co-elementary sets, which implies that the union n equal to 1 to infinity is always co-elementary, is a co-elementary set. So this means that the measure of the union is plus infinity. On the other hand, this sum of these measures is also plus infinity, because each term is plus infinity. So in fact it shows that even if one of them is co-elementary, then you have plus infinity on both sides, and so the equation holds. So even if one En is co-elementary, so let me write not just a disjoint collection of co-elementary sets, but disjoint collection of elementary and at least one co-elementary set, then this means that the union is a co-elementary set, and you have plus infinity on both sides. This implies that countable additivity holds. Countable additivity holds. So now we only have to show case A, in where union of elementary sets is elementary and union of elementary sets is co-elementary. So let's see the proof. So let En be elementary sets such that elementary disjoint sets such that the union is again elementary. So then we have to show that M of the union, because it's an elementary, so M bar is just M, is the sum of the MENs n equal to 1 to infinity. So here we do not have countable subadditivity because we don't know that M is an outer measure. So we have to show countable subadditivity. On the other hand, it's easy to show that since union any finite union n equal to 1 to n En is a subset of the Ens, this implies that by finite additivity that this finite sum of Men is less than or equal to the measure of the union. And so if you this is for any n greater than or equal to 1. Here we have used the fact that the elementary measure is finitely additive on disjoint sets. So here take the limit as n tends to infinity, capital N tends to infinity, n equal to 1 to capital N Men is less than or equal to M of the union. So this is nothing but the limit is nothing but the whole sum. So we get the inequality on one side. The other inequality, if M was an outer measure, would be we would then conclude that the equality holds, but we do not have countable subadditivity, so we have to improvise. So we have to give another argument. So it suffices now. It suffices to show that M of the union is less than or equal to the infinite sum of MENs. So to do this, we proceed as follows. So let me denote this set by E. We will use the fact that the elementary measure has the property of inner approximation by closed sets, closed elementary sets, in fact, closed elementary sets, and outer approximation by open elementary sets. So for E we will use inner approximation, and for ENs we will use outer approximation, and then we will use a compactness argument to reduce to finitely many unions, and then we can use finite additivity. So let's see how this works. So given epsilon greater than 0, there exists a closed set F inside E, closed elementary set F inside E, such that the elementary measure of E minus F is less than or equal to epsilon, and because F is a closed elementary set, it is also a bounded and closed set, which means that F is compact. F is a compact set. So this means that the measure of F is greater than or equal to measure of E minus epsilon. On the other hand, there exists for each n greater than or equal to 1, there exists an open set Un containing En, again open elementary set. We are only working with elementary sets. So an open elementary set Un containing En such that the measure of Un is less than or equal to measure of En plus epsilon by 2 to the power n. So again we are going to use a 2 to the power epsilon by 2 to the power n trick, because there is a sum involved. So then this implies that F is contained in the union n equal to 1 to infinity of Un, because F is a subset of the unions of Ens, and since F is compact, there exists a finite set, finite collection, say U1 up to renumbering. I can say it's U1, U2 up to U capital N, say, such that F is contained in the finite collection of sets Un. So this means that the measure of F is less than or equal to the measure of the union n equal to 1 to capital N U Un, but this is less than or equal to the sum n equal to 1 to infinity 1 to n first, capital N, measure of En plus epsilon by 2 to the power n, and this is less than or equal to, note that here I used finite subadditivity property for this inequality, finite subadditivity property, which follows from finite additivity actually. So then we have this finite sum is of course less than or equal to the infinite sum Men plus epsilon by 2 to the power n, which is nothing but the total sum Men plus epsilon. And on the other hand, this implies that Me minus epsilon is less than or equal to n equal to 1 to infinity Men plus epsilon. So this minus epsilon can be taken on the right side, so you get plus 2 epsilon. Nevertheless, you get the inequality that you want, n equal to 1 to infinity M En. So we have shown this inequality, and we have proved in fact that for a disjoint collection of elementary sets which are whose union is again elementary, you have the pre-measure condition is valid. Now suppose that the union, so all Ens is a collection of elementary sets such that the union E n equal to 1 to infinity is co-elementary. So this means that the extended measure, so these are all so the extended measure is plus infinity. So it suffices to show to show that the sum of m e n equal to 1 to infinity is also equal to plus infinity, which is to say that given any capital M greater than 0, there exists n in the natural numbers such that this sum, the partial sum from n equal to 1 to capital N m e n, is greater than or equal to capital M. So this shows that when you take the limit as n goes to infinity, you get plus infinity. So we proceed as follows. Since the union of ENs n equal to 1 to infinity is co-elementary, this implies that the intersection of the complements n equal to 1 to infinity is elementary. So we can choose an open elementary subset, elementary set U, such that it contains this intersection which is elementary of the complements of the ENs. So in particular we have the elementary measure is finite. So now this means that once you again take complements, this means that the union of ENs is now contained inside the complement of this open set U. Now for any R greater than 0, which is large enough to contain U. U is a bounded set, so we can always find for any R which is large enough so that the ball, the Euclidean ball with center 0 and radius r, contains U. For this R we have the intersection En intersection B0 R. I would rather take the closed unit ball here, closed ball with radius r here, and you will see why. So this is contained in the intersection of the complement of U with this closed ball of radius r, and this is nothing but B0 r minus U, and so this is in fact a closed and bounded set. U is open, so U complement is closed, and this is also closed and bounded. So this whole thing is a compact set K. So therefore this implies that there is a slight mistake here. This should be, the inclusion should be the other way around. So here we have a compact set K which is contained inside this infinite union, but in fact we can discard those sets En which do not intersect B0R. So this compact set K is contained in the union of ENs where n belongs to some index set IR, which is given by the set of natural numbers such that En intersection B0R bar is not empty, because the others, if they are empty, we can discard them. So now if IR has finite cardinality, then we can use the finite additivity property to conclude because this implies that measure of k is less than or equal to so first, if the cardinality is finite, then this is the less than or equal to the measure of a finite union of disjoint sets, which is then equal to the sum over a finite index set by finite additivity, and then you can take the entire sum on the right hand side, and note that mk is equal to mb0r bar minus mu, and this is equal to some constant c which only depends on the dimension d times the radius to the power d minus a fixed constant mu. So as r goes to infinity, mk goes to infinity, and because we proved this for any arbitrary r, this inequality holds for any r large enough. So this means that the sum is plus infinity, because the left hand side becomes bigger and bigger and the right hand side gets pushed to plus infinity. But if it could happen that even with the intersection of a small of a bounded ball, Euclidean ball, there could be infinitely many elementary sets inside this collection En that intersect this ball, so that the cardinality of IR may be plus infinity. So in that case we choose, so given epsilon greater than 0, we choose for each n greater than or equal to 1 an open elementary set Un containing En such that the measure of Un is less than or equal to the measure of En plus epsilon by 2 to the power n. So we are again going to use this compactness trick that we used before in the previous case to conclude here, because then there exists, then k is contained in the union of all these Uns, and this means that there exists a finite collection of Uns such that k is a subset of this finite collection 1 to capital N of Un. So then again we can use finite subadditivity property. So mk is less than or equal to the measure, just as we did before, this is less than or equal to the finite sum mun, which is then less than or equal to the sum n equal to 1 to capital N men plus epsilon by 2 to the power n, which is again less than or equal to n equal to 1 to infinity measure of En plus epsilon. So epsilon is a fixed quantity, so it remains finite. So for example, one can choose epsilon to be 1, in which case this sum n equal to 1 to infinity men is greater than or equal to mk minus 1, and mk goes to infinity as r goes to infinity. So again we get that this sum is bounded above by a sequence of numbers which goes to infinity. So this again means that n equal to 1 to infinity men is plus infinity. So we see that we have finally proved that this proves that the elementary measure m bar on the elementary algebra is a pre-measure, and once we have a pre-measure, then we can use the Hahn Kolmogorov extension theorem to get a measure. Extension theorem gives a measure m tilde on a sigma algebra, which is given by C m star of R D, where m star of E is the outer measure defined using elementary sets. So this is the sum n equal to 1 to infinity m e I, such that E is a subset of EI and EI belongs to this elementary algebra for each I. Of course, if one of these is co-elementary, then we can discard this. So this is an infimum over such things. So we can discard those covers, because then you will get plus infinity on the sum. So in fact, one can show that this is the same as the outer measure that you get from just using boxes, BI boxes. So this is an exercise for you to check that these two things are the same. Therefore, the Lebesgue outer measure and the measure induced by the elementary measure, which is a pre-measure, they are the same, and therefore the final measure is just the Lebesgue measure. So the elementary measure gives the Lebesgue measure on RD via the Hahn Kolmogorov extension theorem.